Alright, so I'm Zach Bussey from 5th period physics IB, Mr. McNeil, and I'm going to be talking about a problem from the second physics problem set for thermodynamics. So let's talk about the problem. And by the way, this problem is going to involve using the ideal gas law, which is pressure times volume is equal to the number of moles times the ideal gas constant times the temperature in Kelvin. Alright, so let's talk about the problem. So it says, oxygen for hospital patients is kept in special tanks where the oxygen has a pressure of 65 atmospheres and a temperature of 288 Kelvin. Alright, so let's write that information down. So, storage. In storage, we have 65 atmospheres for the pressure, which is going to be applied to the pressure in the ideal gas equation. And we also have, let's just do this, I'll show you why. We also have the volume. Later on in the equation it says 1 cubic meter, so 1 cubic meter is equal to the number of moles, and this is applying to oxygen, times the ideal gas constant, times the temperature, which it says is 288 Kelvin. Alright, so the second part of the problem says that the oxygen is pumped into a patient's room, where it's administered at a pressure of 1 atmosphere and a temperature of 297 Kelvin. So the pressure is 1 atmosphere and temperature is 297 Kelvin. Okay, so patient. So 1 atmosphere. Alright, times, and what we don't know in the problem, what we're solving for, is the volume in the patient's room, V sub P, is equal to the same number of moles of gas, because the amount of gas isn't changing, it's just the aspects of it, times ideal gas constant, times 297 Kelvin. Now, the volume is going to change when it's released into the patient's room, and that's why it's different. That's why we have to solve for it. So, in the patient room equation, we have two variables. We have the volume in the patient's room. We don't know that, but we also don't know the amount of the number of moles of oxygen involved. So we have two variables in the equation. So how do we fix this situation? Because we can't solve for one while the other is still variable. Well, it turns out that since we have the other equation, which has the same number of moles, because we said that the number of moles isn't changing when the oxygen is being transferred to the patient's room, we can solve for the number of moles times ideal gas constant, or NR, in both equations, and then set them equal. And doing that, for the storage room, we're going to have NR is equal to 65 atmospheres times 1 meter cubed. I'm just doing that because it's 1, all over 288 Kelvin, because you have to divide both sides by 280 to solve for NR. 288 Kelvin. Now, NR in this equation is the same, so we can do the same type of thing, divide by 297K. And we get 1 atmosphere times the volume in the patient's room is equal to 297 Kelvin. So now we have an equation where there's only one variable, which is the volume in the patient's room. And it's not actually really a variable now, because now we can solve for it. It has to be some kind of constant, at least in this situation. So how do we solve for it? Well, on both sides of the equations there are also different kinds of units. However, since those units are in the same places and they are the same type of units, we can cancel them out on both sides. So we have Kelvin, 1 Kelvin, Kelvin to the 1 basically, on the bottom of each equation, so we cross those out. We also have atmospheres, so let's cross those out as well. So what are we left with? We have 65 cubic meters over 288. It's equal to the volume of the oxygen in the patient's room divided by 297. So, since we only have two different things on this side of the equation, and one is being divided by the other, we can just solve for the numerator. So we multiply both sides by 297. And doing that, 297 basically comes over here, multiply. What you're going to get for VP is about 67.00125 cubic meters. Alright? And that's the problem. That's how much the how much volume that the gas is going to have in the patient's room.